Okay, good morning and welcome. It's an important occasion today here in Milan because we have been running this ranking of the main, most important think tank working on climate change, working on environmental economics, or on sustainability for some years. But the ceremony awarding the best think tank took place in Venice. But this year, given that Milan is a little bit at the center of the world because of the Expo, because of the many events taking place in Milan, we decided to move the ceremony here in Milan. This is probably another reason. The second reason is that we had a sequence of lectures on the Arctic in these last months, and this one is also on the Arctic, and it will be quite interesting. So there is a continuity of events that make reasonable to hold this ceremony here in Milan. But before moving to all these concrete aspects, let me remind you a little bit, in particular for those who are not been here in previous years, what's the prize that we are awarding today and how it is computing, why it is important. Rankings, as you all know, are important. University rankings, for example, have a lot of influence in the decisions of students to go in one university or another one. In the same way, rankings of think tanks and research institutions have been developed in recent years to try to value the work of these institutions, in particular, not only in terms of research, but also in terms of policy support and influence into the policy process. It's difficult to measure these other more qualitative dimensions of a think tank, but still it is important to try and to provide assessments of different think tanks around the world. What we did a few years ago, it was 5 years ago, is to launch an observatory, a system through which we monitor the activities of think tanks all around the world. If you go into the website, you will find a map of the world in which for each country you see which think tanks and research institutions are non-university research institutions are working on environmental economics, climate change economics, and related issues. You can get information about the think tank, you can see the history and all possible links to the activities of the think tank. After a while, we decided that given this amount of information, we could compute an index, an indicator of the performance of these think tanks. An indicator quite different from the other ones that are currently used for other kind of rankings, because it's not based on surveys, on questionnaires, on opinions of experts, but it's really based on the performance of the think tank in different fields. First of all, the academic performance, because we compute the number of publications in top journals and both academic publications, reports for international organizations, and so on and so forth. But also, as I said, impacts in terms of communication, so number of events organized, participation to the major important conferences around the world, and impacts in terms of policy support, in particular participation to the IPCC, lead authors involved in the preparation of the latest IPCC reports, and so on and so forth. So there is a bunch of indicators. These indicators are then aggregated through a quite complicated methodology that many of you know, because we have been used also to compute the sustainability indicators of different countries. And then this aggregate indicator provides a measure of the performance of the think tank and the ranking of the think tanks around the world. We are able to consider more than 250 think tanks. We then focus for the final measurement only on the top 100, because the whole procedure is quite complicated and we need to be very careful in gathering the data. So we focus on the top 100, and then we produce the ranking of the top 100 think tank working on climate change worldwide. One final important remark: most rankings produced for universities, for example, don't standardize the indicators take into account the size of the university, which implies that the biggest ones are more likely to be at the top of the ranking than the small ones. What we do is to standardize indicators and to consider the size, that is the number of researchers working on the indicator, so it's a sort of per capita effective, so per capita performance that we compute in defining the ranking. So having said that, this ranking has been published in June. The results have been presented at the European Conference of Environmental Economists in Helsinki at the end of June. So the outcome is well known, but what we want to do today is to formally deliver the prize to the winner and to listen to the keynote lecture that the director of the winning organization usually comes here in Venice or in Milan to deliver in the day in which the ceremony takes place and the prize is awarded. Today we have here Dr. Goetz, who is the deputy director and senior scientist of the winning organization, which is the Woods Hole Research Center in Massachusetts, United States, which is the winner of this ranking for the second year in a row. They were the winner even a year ago, and for the first time we have the same research organization which has been able to win the prize for 2 years in a row. Just to let you know, the second ranked research institution is a European one, the Mercator Research Institute in Berlin, which is also good news because it's a new and dynamic European institution which is moving up fast in terms of publications, model developments, and so on and so forth, which is why probably they're on the second place. Another reason is probably that they were hugely involved in the preparation of the assessment report, the AR5, the APC assessment report, which implies that this year they've been performing quite well in terms of policy support. But I'm really happy to have here Dr. Goetz. I'm really happy to award the prize for the second time to the Woods Hole Research Center. And before listening to his lecture, I'm very pleased to award him with this is what we have as a prize. Of course, it will be good on your wall. And please join me. Thank you.
Thank you very much.
Great, thank you. And of course, the floor is yours, and we're quite happy to listen to you.
See the lecture?
Yeah.
Thank you. Make sure this is on. Thank you, Carlo, and thank you all, especially the International Center for Climate Governance, for this award for the second year in a row. It really means a lot to us. It's very prestigious, and we're just immensely pleased to be the recipient. So my lecture today will focus on the Arctic. I understand you've had a series of work or presentations in the Arctic. Much of our work at the Woods Hole Research Center is focused on the tropics and has been for several decades. We're celebrating our 30th anniversary this year, and a lot of our work in the past has been focused on the tropics, but more and more we're diversifying our work in the Arctic, and in fact that's what I did my PhD work on years ago. I won't say how many years ago now already, but that's been my focus for some time. And we have maybe 15 scientists at the research center. We're a little over 50 people total, including postdoctoral researchers and research assistants and associates and so on. But several of the scientists there are focused on work in the Arctic, and so I'll give you a little bit of a taste of some of our research in the Arctic. And I think last year, when our acting director, Richard Houghton, presented here, he probably talked more about the global carbon cycle and our work there, which is something we've also been doing for some 3 decades now. So let me just say again how pleased we are to get this award. This is the press release from our organization when we received it. There was, let's say, our board of directors was extremely pleased to see this as well. And we made, as we say in the U.S., we made some hay of it. We let people know about it and reveled in the honor. So thank you again. It means a lot to us. So let me give you a flavor for some of the work that we do. Obviously, I can't go into all of it, and I can't go into any specific aspect of our work in the Arctic in great depth, but let me give you something of a survey for what we'll talk about, which is first, a lot of satellite remote sensing work linked with field observations, much of which is documenting change in Arctic systems. And I'll talk a little bit more about the distinction between Arctic and other parts of the high northern latitudes in a moment. We also do work modeling what's likely to happen in the future in the Arctic in terms of vegetation distribution, so I'll show you some results from that. And then the same type of work, satellite remote sensing, even aircraft remote sensing, and field measurements focused in the boreal forest ecosystems of the Arctic. So of course that's the big band of forest vegetation that stretches from interior Alaska across Canada and across Russia and all the way through eastern Siberia. And we do work in those places, and I'll show you a bit about that. We also have a big focus on permafrost and permafrost measurements, observations, manipulation experiments, and modeling what's likely to happen in the future with permafrost. And I'll give you a bit more of a sense for why permafrost is so very important and why we're focused on it. And then I'll talk a little bit about, more broadly, just the feedbacks taking place in each of these areas, and also how we try to link with policy. A big part of the research that we do at the Research Center is very much oriented towards informing decision-making and bringing science to the policy process. And I think that's probably a significant part of the reason why we've risen to the top here for the second year in a row. So why focus on the Arctic? I think, as most of you know, warming is amplified in the Arctic because of the very large land mass, especially in the high northern latitudes, relative to the southern hemisphere. And as a result of that, we get an amplification of warming, and that's very clearly documented in the instrument record over the past many decades. And this is a gridded representation of warming in the Arctic, where you can see actual observations of what's occurring relative to the rest of the world, with some 4 degrees C potential amplification. And this is one of the results of that type of warming in the Arctic, which is the decline of this polar ice cap, as I'm sure most of you have heard about in recent years. This graphic shows a line of the median extent of sea ice from 1979 to 2000, and then the actual distribution as mapped from satellites in recent years. So obviously a big important indicator, but also a big feedback to the atmosphere and to climate change, primarily through the energy balance changes as you go from a very bright ice-covered surface to a very dark water surface, and the absorption of energy and re-emission of that energy warming the atmosphere. This said, the Research Center does not work on ice caps, and we don't work on mountain glaciers. We focus almost entirely on the land surface, and the rest of what I'll be talking about today is focused on the land surface. And a lot of what we do is based on satellite observations. So this is some work that we've published in different forms a number of times in recent years, where we're monitoring using a time series of satellite observations over about the past 30 years of the satellite record, 30 plus years now. What's happening with vegetation photosynthesis and vegetation productivity. So what this map is showing, all the bright green areas in the map show where vegetation, primarily tundra vegetation in the higher Arctic, is increasing in productivity over the past 30-some years, since 1981 onwards. And so, as you may know, we can use satellites to detect photosynthetic activity. It's just a ratio of spectral reflectance in different wavelengths, high reflectance in the infrared, absorption in the photosynthetically active region. We have different ways to manipulate those reflectances to provide indicators of productivity. But the story here is that the Arctic is greening. And no matter how we look at it in recent decades, no matter which satellite data records we use, it's a very consistent signal in the record. We see this greening. So do I have a pointer by any chance?
Do we have a pointer?
It might be helpful if we can find one, but I think you
but
recognize probably the lay of the continents. On the left side of the screen being North America, tilted on its side. In the upper part of that, you'll see a bright green strip on the north slope of Alaska, north of the Brooks Range. So I'll come back to that area a few times as we go, but that's one area that's very consistently showing this greening trend through time. So these are statistically significant trends as observed in the satellite record. And again, we have a number of publications documenting this, and it's quite consistent. I'll come back to the other areas in a bit. The browning, what we call the browning areas, the darker colors there, and what's happening there in those regions. So what's driving this greening of the Arctic? Many people suggest that it's an increase in woody shrub cover. In other words, the densification and expansion of woody shrubs in areas that are traditionally tundra vegetation, which is a more herbaceous vegetation type. So there are multiple lines of evidence from the shrub record, including long-term monitoring networks, shrub rings, just like we do tree rings, we can do shrub rings and look at incremental growth of shrubs. And manipulation experiments, controlling for different factors. All the red dots in this map show areas where field measurements have documented a systematic increase in shrub growth across the Arctic. The blue dots are unchanging over the record, and the yellow dot, there's only one, are where shrubs are actually decreasing in cover. So what this tells us is there's good evidence that shrubs are in fact increasing in density, in cover, and even in height across the Arctic system. So we're curious, many people are curious, thank you. Is it shrubs that's driving what we see? Is it increases in shrub cover that's driving what we see in the satellite record? So we looked at that by mapping shrub cover on the north slope of Alaska. Let me just go back to point out, I think you probably know, but this is the area I'm talking about, the north slope of Alaska. This, of course, is interior Alaska, around Canada, Russia, all the way up to northeastern Siberia. I'll talk about that area as well in a bit. So this is a map of the north slope of Alaska, areas where we did field work, but also collected very high-resolution satellite imagery. That's what all the boxes on this map are. The blue boxes and the yellow boxes are where we acquired very high-resolution satellite imagery, and by that I mean each each pixel, each cell is just 2 or 3 meters in size. And so in that type of imagery, we can actually see the shrubs very easily, and we can classify them. So we did that. There's a publication on this, because the way we did it is perhaps a little unusual. It wasn't just are there shrubs or are there not shrubs, but it's what's the percentage of each pixel that's occupied by shrubs. So we took the high resolution imagery and used that to map more broadly across the entire region using more of a moderate resolution imagery from the Landsat series of satellites. And now the European have Sentinel satellites that we can also use for this. So we did this mapping, looked at the percentage of shrub cover in each pixel, and then we looked at how that relates to what we see in the longer term trend, the 30-year trend that I spoke about earlier, asking the question, is shrub cover driving greening in the Arctic? And as you can tell from the heading here, it appears not. What we see is that no matter what the percentage of shrub cover is in any given area, whether it's less than 25%, 25 to 50, 50 to 75, or above 75% per pixel shrub cover, no matter the density, we see this very systematic increase through time in greening, in vegetation greening from the satellite record, no matter what the shrub density is. So that tells us that it's not only shrubs that are increasing in vegetation productivity and cover, but it's the rest of the tundra system as well that's increasing in productivity. And there's a lot of research now, as you may know, to get a better handle on that, to document how much tussock tundra and other herbaceous parts of the Arctic system are greening relative to shrubs. So let me talk now a little bit about the transition zone between boreal systems, the boreal forest, and the Arctic tundra. Excuse me, I'm just getting over a cold. The black line around this image is what's considered current tree line, largely defined by the extent of something called the Circumarctic Vegetation Map, or CAVM, C-A-V-M, and I'll show you more about that. But so this black line is what's currently considered the extent of tree line, or the transition between boreal forest and Arctic tundra in the current mapping extent. So what we did was look at a lot of satellite imagery, time series again, this time from higher resolution, from moderate resolution imagery from the moderate spectrum, MODIS instrument, which is a moderate resolution imaging spectrometer. So this map is essentially showing you the green places where, or percentage of tree cover. So of course in the southern part of the boreal, tree cover is denser. You see that all across the Circumarctic region. And then there's a lower percentage tree cover as we move up closer to the extent of tree line, which is where you'll see a tree, the most northerly most extent of tree cover. So they may not be very dense. There may only be a couple trees, but that's the northern extent of tree cover. But when we have satellite data, we can think about mapping tree cover in a completely different way. It's not just above 66 degrees north, and it's not just where there's currently tundra, but we can look at it more in a biophysical sense by using satellite data. So all the red boxes on here are transects, where we can look at the gradients of tree cover or vegetation cover, as well as their overall surface reflectance or reflectivity or albedo. So let me talk a little bit about that. This graphic shows as we move away from that tree line defined by the Circumarctic vegetation map. So here's that 0 point here. That's the dotted line. As we move away from that in mostly a southerly direction, 100 kilometers, 200 kilometers, up to 900 kilometers distance from tree line, we see very clearly these large gradients in tree cover. So let's start with that one. That's the middle graph here, this tree canopy cover. We see something like median of about 75% tree cover, 900 kilometers from tree line. And then, of course, as we approach tree line, that tree cover systematically, gradually declines until we hit what is currently tree line. And in fact, you see in this satellite imagery that it does drop precipitously at that point, and you see almost no tree cover beyond what is currently that circumarctic vegetation map boundary. Conversely, if we look at albedo, in other words, the overall reflectance of the surface, mostly in the shortwave wavelength, shortwave albedo, this is the reflectivity. So ice would be 1, almost 100% reflectance. Very dark vegetation is closer, in this case at the southern boreal, about 20 to 25% albedo. And then, of course, that increases as tree cover increases or decreases, albedo increases. And you see even a bit of a jump here again as we move above tree line. And also shown on the map here are just land cover types at the very top. I'm not sure how well you can see those, but the classes are water, forest, shrub, herbaceous, and other. So just to give you some idea. Also shown on the map are these symbols, these triangles, and that is how current Earth system models, on average, represent tree cover and albedo in these systems. So you see that there's not nearly the variation that we see in satellite data. We capture all that variability in satellite data, whereas the models really don't represent that very well. And you see even above tree line, where there are no trees or very, very few trees, that current models approximate 20 or 30% tree cover. So this is clearly an area where we can improve Earth system models and better represent what's happening there. These are largely areas where vegetation is dynamically simulated, suitability, related to the suitability with climate. And then albedo, again, there's also this discrimination. Well, it's not represented terribly well in the Earth system models either. There's a lot less variability, even if we look at the range of models. So albedo is not very well represented either. Especially in this distinction between spring albedo, the gray colors here, versus the dark line, which is summer albedo. So not surprisingly, as vegetation greens up in the summer during the growing season, much of the boreal forest and tundra systems appears quite dark in terms of reflectivity. But in the springtime, when there's snow on the ground, there may be leaves off the trees and deciduous systems, you see much higher albedo, especially as we get up to northern areas with much sparser woody vegetation cover. So this is important, and we need to do a much better job modeling it. So what's likely to happen in the future? We've done some work simulating that, informing models with satellite observations to try to improve this modeling situation. So to ask some questions like, how important is plant productivity in these regions relative to other processes? In other words, the carbon that's taken up through photosynthesis and sequestered in vegetation biomass, how important is that relative to other factors in terms of being a feedback to climate? Does it matter even if it's shrubs or tundra vegetation or tree cover that's driving change that we see? And then a really important factor, which I won't go into a great deal today for Arctic systems, is disturbance, especially fire disturbance. But I'll touch on it briefly. So this is currently how vegetation is mapped across the Arctic region. So this is that map I mentioned earlier, the circumarctic vegetation map. This is an effort that was conducted by scientists all around the world, probably more than 100 vegetation scientists who got together, used just a base map of satellite imagery, and then interpreted it. So this is expert mapping based on a fairly simple process of interpreting vegetation reflectance. And the classes in this map, again, this is for current period, obviously, because it's based on satellite data interpretation of it. The classes of this map range from all the G classes here, the reds and oranges are graminoids, so grassy type vegetation that you find in tundra regions. The P's are prostate shrubs, in other words, low-lying shrubs close to the surface. And the S classes, these blue and purple, are erectophile shrubs, in other words, taller shrubs. And the green classes, which you don't see any of in this particular map, is tree cover. A couple different classes of tree cover, whether it's a mix of sparse trees or other more advanced tree cover or vegetation, tree cover vegetation. So this is what the map currently looks like. Again, just to orient you, because it may not be obvious in this, and it's flipped around from the previous map. Here's the north slope of Alaska here. And we go across northern Canada above Hudson's Bay, Greenland, of course, Europe, Eastern Europe, all the way across Siberia to northeastern Siberia. So just to orient you relative to the previous maps. This is what we predict that will look like in 40 years. And there are some pretty dramatic changes. This is a paper published in Nature Climate Change maybe 2 years ago now. And we ran many, many different scenarios. We informed this modeling effort with many different scenarios based on representative concentration pathways of the IPCC, and looked at what the variability was in those. We also considered dispersal, whether dispersal of trees from the more southerly boreal areas into the Arctic would be restricted or unrestricted, equilibrium dispersal. And in fact, this representation is for that equilibrium dispersal because we think there's pretty good evidence. We know there's pretty good evidence from other systems and from the observations that we do have that dispersal, especially of boreal trees, many of which have windblown seeds or are dispersed by birds that migrate on their path through the boreal to the Arctic systems, that dispersal won't be a limiting factor. But this is what we predict it will look like, and what you immediately will recognize is the bright greens in many of these areas moving in. I'll zoom in on some of these areas shortly to give you a better sense for it. But clearly, as we move from current system to a system 40 years from now, we predict quite dramatic changes in vegetation cover, especially this movement of trees into what is now Arctic system, Arctic vegetation without much tree cover. So here's a little bit, to give you a bit of a better sense for it. Again, north slope of Alaska here, which is largely graminoid, tussock tundra systems. You see below, there's a mountain range here, the Brooks Range, that separates the north slope from the rest of Alaska. Below the north slope currently, there are trees, quite dense tree cover in some areas. And what we see are those trees actually moving across what's currently tree line into the north slope of Alaska. And the same in northeastern Siberia, and we have field sites, and we work in northeastern Siberia, and we have for the past decade. We see this movement of trees into tundra systems. So that doesn't mean that suddenly we will have a dense boreal forest in what is now tundra. It might look more like what you see in the photograph here, or maybe not even that robust. In other words, there'll be some trees present. They won't be very dense. They'll probably be pretty skinny, scrawny, black spruce, for instance, dispersed across the tundra. So it might look something like what you see in that image currently. When some reporters picked up on this publication and they showed the transitions that we're talking about here, going from ice fields to a lush tropical forest. So that's not quite the idea. It's really just that there will be trees present, and those trees will change the system quite substantially, largely because they will change the reflectivity of the surface albedo. So that's what these maps are showing. From the current system, again, it's the same maps: North America, North Slope of Alaska, northeastern or northern Eurasia, current period and in the future. And what you see is that the presence of trees and the densification of shrubs will make that a much lower reflectance surface. So the albedo will be decreased as a result of these changes, and that in turn changes the whole energy balance equation. So for example, if we just look at a simple metric of energy balance in the Arctic, the net surface shortwave radiation, in other words, in the visible infrared, mid-infrared region, that lower albedo will increase net shortwave radiation quite substantially, proportionally. In other words, these dark trees will absorb a lot of the energy from the sun. They'll retain that energy, radiate that energy, and that warms the surface. And shrubs have the same effect, this dark woody vegetation. They're darker, they warm the surface, and that changes the entire energy balance. Excuse me. And hopefully you can see this better than I can on the screen here, but this is what it looks like if we jump back out to the entire circumarctic region. Substantial decreases in albedo all around the Arctic, and substantial increases in that shortwave radiation associated with these changes in vegetation cover. So what this tells us is, in fact, feedback to climate from the Arctic system will largely be in the terms of, as a biophysical medium, modifying the energy balance. And the forcings, the radiative forcings, by comparison of vegetation productivity, how much carbon they take out of the atmosphere as they increase their growth, or how much water they transpire to the atmosphere through evapotranspiration, are really small factors by comparison to these changes in the surface energy balance. So that's going to be the big factor that changes feedbacks to climate. In terms of disturbance, we're seeing a lot of evidence of increased fire disturbance in the Arctic. This is an example of a fire captured on the North Slope of Alaska. The fire took place in 2007. It's called the Anatuvik River Fire. It's about 130 kilometers long and about 30 kilometers wide. It burned from May into early October, and in fact the fire stayed in these organic soils, and some of it burned right through the winter. So really what seems to be almost an unprecedented event in terms of fire disturbance in an Arctic system. And of course that changes everything as well. That changes the albedo and the vegetation and the energy balance quite substantially. Here's what the fire looks like. Immediately after the fire, we were able to get some support to go in and put carbon flux and energy balance towers here, and to establish vegetation plots, and to immediately start to monitor what happens post-fire. So that work is ongoing. But quite a large fire. This is now shifting more to boreal systems. This is an article that recently appeared in Science that documents some of the work that the Woods Hole Research Center, myself, and colleagues have been looking at in terms of fire disturbance, which they characterized as the new north. So let me shift now to boreal systems. And what we see there is really quite different than what we see in the Arctic tundra regions. It's much more of a evidence for declines in productivity. So what this map now is showing are only those areas that have above a certain amount of tree cover, above 20 or 25% tree cover. So this is only where trees are present. There are places where we see greening, especially in the eastern part of northern Eurasia, Eastern Europe. and the Yamal Peninsula, those areas. But a lot of what we see in North America are these browning, and we're very interested in knowing why would, when all the models predict that boreal forests will increase in photosynthesis and productivity through time, why would in fact satellite observations tell us something different? And we think there's quite good evidence that this is really driven by drought. Not so much soil moisture drought, which we typically think about, but really the drying power of air, very hot, dry air masses that are restricting vegetation photosynthesis. And in fact, what we see in the satellite record is reflected in tree ring records. This is a map showing for Alaska. Again, here's the north slope of Alaska, a lot of greening going on there. Very different story in the interior of Alaska, where the satellite record, which are all the tans and browns in this map, show declines in productivity over the past 30 years. And in fact, the tree ring records see that as well. All the circles and triangles or all the circles and triangles on this map show where we have tree ring records characterizing forests, and we see systematic declines in productivity reflected in the tree ring record as well as in the satellite record. So this is nice corroboration of what we're seeing from space is in fact happening on the ground. The only place we see increases in productivity or greening in boreal vegetation is on these coastal areas, which are much more mesic and wetter, so they're not as influenced as the interior of Alaska to these hot, dry air masses. And as another aspect of what we would expect to happen in these boreal systems, as productivity declines through time, year after year, we would expect to see trees dying off. And so this is just a graphic representation of that on a rainfall from wetter to drier and temperature from cooler to warmer gradient and envelope, where we expect future climate to move the entire system towards a more drought-intense, drier, warmer area where we'll see much greater increases in tree mortality. There's already pretty good evidence from this from field measurements, and we're actually seeing evidence now that we're picking this up in the satellite record. So this is some work that we've done for sites distributed across North America, all these blue dots in Alaska, all these other colored dots. These are permanent sampled tree plots where people are monitoring what's happening with trees, how many of them die through time over many years. So these are our field measurements that we then relate to satellite observations, and in fact, we're seeing pretty good evidence that we can pick this up in the satellite record. So just quickly, I won't go into great detail on this, but these are a couple different satellite records. This is what the GIMS 3G, so this is mostly the images that I've been showing you, 30 years of satellite observations at a fairly coarse resolution, about an 8 kilometer grid cell size resolution. And then this is from the MODIS instrument, which is only 250 meters, so much higher resolution. But in both of those cases, control plots are in blue. Areas where we see mortality are in this orange color. We see this decline preceding mortality events in vegetation productivity. And that's captured not only in the coarse resolution satellite data, but especially in the moderate resolution satellite data. So these declining productivity through time ultimately increases the likelihood of mortality. Fire in the Arctic system is a big factor. Fire is a normal, natural part of the system. It's ubiquitous. It's always been part of the system. The trees in these boreal forest systems are adapted to fire. This is a map of where fires have actually occurred in recent decades from 1970s onward, and it's a large part of the landscape. But the trees are adapted. In fact, many of them have serotinous cones, so when they're subject to heat, they open up and disperse their seeds and regrowth occurs naturally. But what we're seeing in these systems now is much more severe burning. This is a picture of a set of fires that took place in the Northwest Territories in Canada. in 2014. Just giving you some sense for how dramatic these fires are. It's not just the trees that are burning, it's the soil burning off, the organic soil, the peatlands that actually burn. And when that happens, it changes what's likely to happen over the next 30-some years. So this is just a representation of, at the top, a fire that burns off the soil cover, so that the organic soil cover, so you're down to more mineral soil, and what happens, what we see happening very systematically on the ground, if fire's not very severe, the soil's not burned off, it pretty much comes back as what it was, which is in North America at least, a largely evergreen conifer system. It'll go through a deciduous phase, but it ends up being largely a conifer system, stays a conifer system. Conversely, where it's severely burned, we see very systematic return to deciduous vegetation cover, and that persists for decades. And of course, that changes everything. It changes the productivity, the nutrient cycling, the albedo, the energy balance, and it sets the system on an entirely different course than what it was before. And again, that persists for decades. So fire is really dramatically important, especially severe fire, and we're seeing a lot more severe fire. It also, because we're burning off that insulating soil cover, it has a big effect on permafrost. In areas where that insulating soil is burned off, permafrost can thaw quite dramatically, and you see a landscape that looks something like this, where the ice melts out, ice that's been frozen for decades thaws, and you get these very wet surfaces. So fire permafrost interactions are a very active area of research at the research center and more broadly as well. And permafrost is a big deal because it covers much of the northern high latitudes. This is carbon that's been accumulating for thousands, tens of thousands of years. It's currently locked up in a frozen state, but with warming, and especially with fire, that changes, and we see big pulses of carbon coming out of the system when the permafrost thaws. So currently, permafrost covers about 25% of the northern hemisphere. It's quite substantial. And just about every model predicts significant declines in permafrost over the next 50 to 100 years. So again, this is just scenarios from the representative concentration pathways of the IPCC. No matter what model you look at, declines in permafrost, and that has big implications. So this is the feedback cycle. Thawing puts a lot of CO2 and methane into the atmosphere. That produces climate warming, and that produces additional thawing. So that's a positive feedback. Not a positive thing, but a positive feedback. And what's likely to happen then? What's the magnitude, timing, and form of how permafrost is likely to change? There's a tremendous amount of interest in this now because the potential for warming the atmosphere is enormous. So just to give you some sense of that, from 1850 to 2005, this is the amount of carbon that's been emitted into the atmosphere from fossil fuels, about 365 gigatons or petagrams of carbon. That's the same thing, gigaton, petagram. Released from fossil fuel emissions, another 150 from land use change. What we expect to happen based on expert surveys because we don't have enough sufficient information on this currently, we go with expert surveys from people who work in permafrost regions. They estimate about a 7 to 11% loss of permafrost, and that translates to somewhere between 120 to 195 gigatons of carbon. So more than has occurred from land use change, deforestation, forest degradation over the past 155 years is likely to go into the atmosphere under our best expert opinions by 2100. And even more when we consider methane in terms of CO2 equivalents. So very substantial. How does this affect what we're currently negotiating in the policy arena in terms of emission targets? Let's say, as many people are, that we want to stay below 2 degrees C. That's our target in terms of acceptable warming. Some people would argue that even that is not acceptable. So that puts a ceiling of about 790 gigatons on us. To date, we've already emitted some 515 gigatons. There's 275 remaining. Permafrost will be, under these expert opinion scenarios, at least 160 gigatons of that. So we're currently going to United Nations Framework Convention on Climate Change talks and trying to meet a target of 275 gigatons maximum, having already committed to 515 when we're not even thinking about 160 gigatons of carbon coming out of the permafrost pool. So that's a knowledge gap which we're trying to bring awareness to more and more and focusing very heavily on. And we'll have a side event at the Conference of the Parties, the 21st Conference of the Parties in Paris coming up in December, to try to raise this awareness of the importance of permafrost. Of course, there are many other ecosystem impacts. It's not all about carbon. It impacts the vegetation, it impacts the fauna, and that in turn impacts the people who rely on the fauna, especially native people. It impacts infrastructure, causes roads to sink and deform, and pipelines and houses to sink and so on, even collapse. So it's a big deal in terms of costs of infrastructure damage. So just to summarize, climate change is greater and more rapid in the Arctic than anywhere else. Predicted warming and feedbacks will largely occur as a biophysical medium, in other words, through the energy balance. Recent warming has created a host of changes which I've talked about: vegetation productivity, tree mortality, changes in albedo and energy balance, intensification of the fire regime, and we think that drought, especially these warm, dry air masses or high vapor pressure deficits, are what's driving much of this. And fire and vegetation changes that we're seeing are pushing the system in the wrong direction. They're pushing it towards positive feedbacks that will mobilize permafrost carbon to the atmosphere. And this is what everyone is thinking now of in terms of a potential tipping point. Some of the tipping point jargon is not liked by many, but the freezing point of water between an ice and a liquid state is a very real thing. And if we cross that threshold, we go from ice to water and changes everything. So it is, I think, fair to say we can think of permafrost systems as a potential tipping point. So this is a graphic that I worked on for the IPCC 5th Assessment Report, Working Group 2, just summarizing all this stuff I've talked about. From fire, boreal forest change, tree mortality, shrubification, permafrost thaw, and so on. So this is in the Working Group 2 report. So the end is near. I'm almost done. Thank you for your patience. But what I wanted to do too is just touch on a few policy hooks towards the end here, which I know many of you are interested in. There's a great deal of focus on the Arctic now, not just in the science aspect of it, but in the policy aspect of it. So of course there's the Arctic Council, which the United States is chairing now. That consists of 8 Arctic nations, a much broader group of nations which have interests in the Arctic. So they don't have land holdings in the Arctic, but they may exploit the resources of the Arctic, which is, of course, on all the policymakers' agendas and radar screens these days. The Global Arctic Leadership Forum, also known as Glacier, is many leaders of Arctic nations. As many of you probably heard, they convened recently in Fairbanks, Alaska, and President Obama and Secretary of State John Kerry addressed them. I'll tell you a little bit about what they said. There's also this group of Arctic 21, which is a group of NGOs that we work with and interact with to try to bring Arctic science to the policy arena. Of course, there's the COP21, which I mentioned, coming up in Paris soon. We'll have presence and side events there. And then there are many native people's organizations and management agencies who are also very much interested in and engaged in the policy of climate change in the Arctic. This is a bad photo of me and some of my colleagues visiting the State Department recently, a few months ago, before President Obama's visit to Fairbanks, to try to bring to them, because again, John Kerry is Secretary of State and Chair of the Arctic Council, to try to bring to them this information that what's happening, especially in terms of permafrost change in the Arctic, really needs to get on the policy agenda. So we visited the Special Representative for the Arctic region and some other key players in the State Department, and we brought this story to them. That was timed before the President's visit, and in fact, you see here a photo of President Obama and Secretary of State John Kerry at the glacier meeting in Fairbanks, and here's what President Obama had to say. You can read it, but I'll read it to you. And we were very pleased to see this. Permafrost stores massive amounts of carbon. This is what the president's saying. When the permafrost is no longer permanent, when it thaws or burns, these gases are released into our atmosphere over time. That could mean that the Arctic may be a new source of emissions that further accelerates global warming. So thank you, President Obama, for bringing that to the arena. And then in the conference that followed from all these policymakers, they issued a joint statement that says, we call for additional research to characterize the response of Arctic permafrost and other carbon reservoirs to warming, especially in hotspots that have the potential to release particularly large stores of greenhouse gases. So in other words, where is permafrost most vulnerable? So this is on their agenda now, and we're very pleased to see that again. So just a little bit more about what we might be able to do about this. The Woods Hole Research Center is largely a scientific organization, but all the science we do is intended to influence and inform policy, as I said. So some of the other ways we work through that is through the science policy side. So we interact with members of the International Arctic Research Commission. We interact with a consortium called the Research Coordination Network focused on permafrost carbon. There's an International Tundra Experiment. There's something called Shrub Hub. These are all networks of scientists around the Arctic. And we also influence Arctic science policy in the U.S., for example, through the National Science Foundation Arctic System Science Program, where one of our scientists was a program manager on leave from the research center for a couple of years there, through the Department of Energy's Next Generation Ecosystem Experiment in the Arctic, and through something called NASA Above Arctic Boreal Vulnerability Experiment, which I am the science lead on. And we just had after 5 years of planning for this interdisciplinary field campaign, which will run for 10 years at about $100 million effort, we finally have underway as of last week, and I'm coming directly from there without having gone home, the first science team meeting of this Arctic Boreal Vulnerability Experiment. So that will allow us, through dozens of teams of scientists working interactively and in an interdisciplinary sense, to put much better numbers on what I've talked to you about today, and to consider which part of the Arctic is most vulnerable. And this is not just the carbon cycle and energy balance side of things, but all the way down to how will it influence people who live in the regions and native peoples, and we are working with them. So with that, I thank you very much for your attention, and especially for this award.
Thank you very much. And if you have questions or remarks, we have a few minutes for comments, for questions from the floor. Anyone? Both on the science and on the policy, because even the policy that mentions what Scott just presented is very important. For example, you mentioned the carbon budget, the remaining carbon budget. We had 275 gigatons. and 160 are going to be consumed possibly by permafrost. However, we produce about 10 gigatons per year. So in any case, we have 27 years in front of us. And for sure, we're going to consume all these carbon budget, whatever we decide in Paris. And if we have the permafrost issue in front of us, the problem becomes slightly more complicated, but it remains there. And the real issue is how to remove CO2 from the atmosphere if we want to meet the 2-degree target.
Yes, to remove it from the atmosphere, for example, by avoiding deforestation in the tropics, or by restoring forests in the tropics where they don't currently exist or were deforested in the past. That's certainly true. If we start to think about atmospheric manipulation and those type of approaches, I think we have to be very careful about how we go about that. And a recent report from the National Research Council reached the same conclusion in terms of any sort of scheme that would, for example, change reflectivity of the atmosphere or other types of really large-scale manipulation experiments. They've warned, and I think rightly so, that we have to be very cautious about approaching anything that way. At the Research Center, we think a much better approach is to focus on restoring the biosphere, to avoid deforestation in the tropics so that it takes so that those trees take a lot of the carbon out of the atmosphere, as they do if we don't remove them or degrade them, and also to think about how to bring forests back to many areas where they have been removed, because that can have a very significant effect. It won't solve the problem, we realize, but it will certainly buy us time to cut fossil fuel emissions, where I think it always comes back to. We need to cut our mining of fossil carbon and emitting it into the atmosphere. So I think that's where our priorities should be. And in fact, I didn't say it, but what these numbers suggest for permafrost are carbon emissions equivalent to another United States on an annual basis. So pumping another United States in terms of atmospheric emissions, and that's something that I think should get everyone's attention as well. That's a big number.
Yeah. There is, however, a lot of uncertainty beyond the numbers that you presented. Last week I was in New York. Jim Hansen presented his latest results showing that ice melting is occurring much, much faster than what we were expecting a few years ago. So uncertainty goes both directions. We could be too optimistic or too pessimistic. In reality, we've been too optimistic in the last year as far as the art is concerned. So what's your assessment of the uncertainty beyond the predictions?
I think you're right. There are significant uncertainties, and I think I gave a little bit of a sense for that in some of the Earth system model representations of vegetation feedbacks. The models are also not strong in the area of simulating permafrost loss. They might capture the aerial extent where permafrost is likely to degrade, but they don't do a very good job of estimating the amount of carbon that comes out. So that's really an active area of research. I mentioned this Department of Energy experiment, next generation ecosystem experiment. That's really the focus of that activity. And this above activity as well is really a focus of that, to improve representation of these processes in our system models and to reduce uncertainties. That said, as you point out, we may be underestimating the rate at which permafrost is likely to degrade, as we did with estimating degradation of ice sheets, and as we appear to have done with methane emissions. So if anything, we really need to represent the models, not only because they need to be improved, but because it's quite possible that we're not capturing just how rapidly things may go towards the worse rather than the better. And so conservative models are great, and the whole IPCC process is a very conservative process, but we need to be aware that things can actually change much more rapidly.
Other questions? Andrea.
Curiosity from somebody who doesn't know anything about the science of this. So I'm quite like also the science of this. I have scientific curiosity about how you, how long it takes, how awareness of this, the magnitude of this risk connected with metric storage, and how the storage, the research on these things.
Okay, now it's working. Okay, so to repeat my question, I'm a layperson, and this is scientific curiosity from somebody who doesn't know a lot of the science of this research. But how long did it take, and what were the key switching points by which you came to realize the magnitude of the gravity of this problem, in the sense that we know what is the freezing point of water, we know where the permafrost is pretty much, and this has been known for a long time, but to make all these links coming to get the awareness that will be could be a cause of a tipping point, which were the technological change, innovations that brought you to understand, or the science of this, to understand the seriousness of this problem along the history.
So the question is what brought me or us at the research center to this realization?
Yes,
I think we've known for quite a while that permafrost has the potential, permafrost thaw has the potential to be a big problem. We just didn't realize quite how large it could be. Some 20 or more years ago, I remember some people, eminent scientists, talking about the permafrost carbon bomb. And at that point, it was really based on the fact that we know there's a tremendous amount of carbon stored in permafrost, but we didn't really have a very good sense for how quickly that could degrade. So organizations like the Permafrost Carbon Research Coordination Network, which I mentioned, the whole focus of that activity is on not only the extent of permafrost that's likely to degrade, but what are the factors that cause it to degrade and at which rate. So I think, and that depends on the lability of the materials, how quickly they're decomposed by organisms, how much methane they release. It also depends on properties of permafrost. What's the ice content of permafrost? In areas, many large areas in northern Eurasia, especially in what they call yedema soils, there's tremendous ice content there. So when that's what really matters in terms of permafrost. What's the ice content? Because that's the tipping point. When the ice melts out, the system collapses, produces what we call thermokarst, and then the carbon comes out of that. So that's really been, I think, as you point out, we've known about permafrost carbon for some time, but what's really driven this sense of urgency in terms of getting that information to policymakers is this realization that it could happen much more rapidly and have bigger numbers than we thought in a fairly relatively short time frame. So by 2050, only 4 decades from now, we're looking at pretty significant numbers of carbon emission to the atmosphere. So I hope that answered your question.
Other questions? Let me address a final one, then we will stop. We've been talking about the risks, the costs, the problems rising from warming the Arctic and ice melting, permafrost thaw, and so on and so forth. Well, we should probably mention also the benefits. You want to understand the role of President Obama, the Glacier Conference, and all countries involved. We should probably consider the interest of those who believe they can gain something out of what's happening over there. Think of the new routes for shipping, new resources that become available, and so on and so forth. What do you think about the benefits?
What do I think about the
benefits from ice melting?
the benefits? Well, that's a tough one. I think, of course there will be economic benefits, but really it's a catch-22, isn't it? When we have increased access to shipping and resource extraction in these regions, it's a very sensitive ecosystem. If we have spills associated with shipping, we'll have a lot more black carbon emitted from shipping as more and more ship traffic moves through these areas. We have black carbon that gets deposited on the snow and ice that speeds the degradation process. And ironically, we'll be extracting a lot more resources, including fossil carbon. So I don't see a lot of benefits other than dollar benefits. And if we use the dollars that come from that to address the problem, then maybe we'll get somewhere.
Yes, I would like to ask you about the local level and the policy makers at the local level. If I think all we know about the tension between productivity, economical productivity, and environmental governance. Do you think in some examples where really there is a synergy between technology, economy, and policy at the level of policymakers, and overall in the region of the tropics? So because you addressed before, maybe the reforestation on the tropics is an addressing point in the future. So do you see any examples at the local level?
That's a really good question. That's a tough one. In the Arctic, as you were asking the question, I was thinking in the Arctic, and it's difficult for me to come up with some real specific examples. But in the tropics, the research center has worked for many years, especially in the Brazilian Amazon, but also in the Democratic Republic of the Congo, to work with local communities to actually try to implement reducing emissions from deforestation and degradation, RED, in the UN policy arena. And that's a tough problem, because of course we have to make sure that the livelihoods of people in these areas are preserved and enhanced, that they can make a decent living and that they have good health benefits, health care, and education. And that has to be a priority, and yet that has to fit within the framework of no longer removing forest as they traditionally do to survive and to grow crops. And so the pathway to do that is through compensation mechanisms, as I'm sure maybe perhaps some of you in this room work on that topic. So what we're trying to do with programs in Brazil and in the Congo is to see what mechanisms work to actually implement these compensations for people who live really a very marginal existence, just growing crops from very small land holdings. But we think there is potential to do good there and to do it well. There's a lot of skepticism that the RED mechanisms will ultimately be successful, but I think there are pathways, as long as it might result in lifestyle changes somewhat, but if there are resources coming in that allow people to at least maintain their livelihoods and to have education and basic health care, then there's the possibility for success. And so the areas that we work in the Congo, which is a very difficult place to work, Brazil's paradise by comparison. In the Congo, we work in an area called Bandaka, which is a couple-hour flight up the Congo River, and really on the frontier of deforestation along the Congo River in central Congo. And that's where we're trying to actually put this process into action on the ground and assess the potential for success of RED. So I hope that answered your question.
Okay, thank you. Thank you very much. And there is a lunch offer for all of us, but before going to lunch, let's congratulate again Dr. Goetz. Thank you.
Thank you.